Okay, so in Module 4f now, we're going to take a look at confidence intervals and hypothesis testing for two different populations. One form of hypothesis test is to test whether the means of two different populations are the same or different, and the other is to test whether proportions in two different populations are the same or different. Basically, everything is just written down in this module, so I'm going to end up just reading the slides to you, which is not going to be very fun for any of us. Here we go. Okay, so we want to take a look at two population tests and show you how to use ISLE to conduct these kinds of tests. Okay, so I'm just going to read this. There's nothing else to do. We often want to make inferences comparing some parameters, such as the mean, of two different populations, such as whether the mean of one population is or is not equal to the mean of some other population. We're going to assume that we have some appropriately gathered random sample of appropriate size from each population. All right, so as an example, this is taken from our fast food experiment. The average calories consumed by 331 people who did receive calorie information was 755 calories with a standard deviation of 241.1 calories. 306 individuals did not receive calorie information, and their calorie consumption was 816 calories with a standard deviation of 246 calories. Now, can we draw any conclusion from these two different samples, these two different populations, those who did receive calorie information and those who did not? Can we conclude that giving people calorie information reduces calorie consumption? Okay, now this is not, by the way, this is not literal data from the fast food test. This is analogous to the fast food test, but we know from looking at the data that in the actual data, there were an approximately equal number of people who were given calorie information and who were not given calorie information. So here we've got one sample size is 755 and the other sample size, whoops, I'm sorry. Oh, my mistake. One sample size is 331 and the other one is 306. So this may, in fact, it probably is from the actual data set. All right, so mu1 is going to be the calorie consumption of people who were given calorie information. And mu2 is going to be the average calorie consumption of those who were not given calorie information. And what we're testing here is our null hypothesis is that the difference between these two means is 0. That is, our null hypothesis is that providing calorie information or not providing calorie information has no effect, no statistically significant effect on the difference in calorie consumption. Our alternative hypothesis here is that mu1, the mean of those who did receive calorie information, minus mu2, the mean of those who did not receive calorie information, that difference is statistically significantly negative. And in fact, we're using a very strict alpha for this test of 0.01. Whoops. All right. All right. So, question. Are we trying to do a one-tailed test or a two-tailed test? And the answer is we're trying to do a one-tailed test here. Our alternative hypothesis is that the mean of those who did get calorie information is less than the mean of those who did not. So in other words, mu1 minus mu2 is less than 0, and that's a one-tailed test. What is the z value? Well, our alpha is 0.01, and we can just look up the z value. And what we get for the right-tailed or equivalently left-tailed test is 2.3263, which is being rounded here to 2.33. The tail that forms the rejection region is this left-hand tail. If our computed z-score is less than minus 2.33, we will reject the null hypothesis. Now the question is, how do we compute the z-score given that we have two different populations? And this is going to look complicated. All right, the standard deviation that we have to use is this nasty looking thing, the square root of the quantity S1 squared over N1 plus S2 squared over N2. And that will give us our z-score. Now, where the heck does that come from? Let me just give you a really quick, hasty description. Let me pull up my document camera here. Come on, document camera. I know you're there. All right, why won't you focus? There, okay. Now it's focused. All right, so this is simply a feature or a fact about the normal distribution. If you have some random variable, x1, that is distributed normally with some mean, mu sub 1, and some variance, sigma squared sub 1, and you have another random variable that's also distributed normally with a different mean and a different variance, then it turns out that the sum of these two normal random variables is distributed normally with a mean of mu1 plus mu2 and a variance of sigma 1 squared plus sigma 2 squared. Okay, and this can just be, proven mathematically that that's the case for a normal random variable. What does that have to do with us? Well, we are comparing a difference of means, mu1 minus mu2. So what we're doing is we are testing whether mu1 minus mu2 is equal to 0. That's our null hypothesis. Or less than 0. That's our alternative hypothesis. Effectively, what we're doing here is we're adding together these two normal distributions. Now, they're normal distributions because of the central limit theorem and because our sample sizes are large. How are we justified in concluding that adding to normal distributions is the same, gives us the same variance as subtracting one normal distribution from another. Well, if I say x1 minus x2, this is the same thing as saying x1 plus the negative of x2. Okay, and the negative of x2 is just x2 flipped around 0. Everything is a mirror image. The negative of x2 is the mirror image of x. And that mirror image of x is going to have a negative mean. So we take the mean and get the negative. But the variance of that mirror image of x is going to be the same as the variance of x, or of x2 in this case. All right. So when I do this test of whether the mean of one normal distribution is equal to or less than, or the mean of some other normal distribution, the variance computation remains the same, and the standard deviation is just the square root of the variance. Okay, so there is a mathematical reason behind this sort of arbitrary looking formula. Okay, so our estimates of of sigma is going to be the standard deviation squared over the size of the sample for the random variable x1 and also for the random variable x2. So I just take the square root of that sum. Easy for me to say. All right. Okay, let me pull back up my... There we go. Okay, so, there is an explanation for this. You can just memorize the formula. So our z-score is going to be the sample estimate minus the null hypothesis value divided by the standard deviation of the sample estimate, which is this formula. All right, so x1 bar, or x bar sub 1, estimates mu sub 1, and it has a standard deviation of s1 squared over n1. X bar sub 2 estimates mu 2, and it has a standard deviation of s sub 2 squared over n2. And therefore, x1 minus x2 is an estimate of mu1 minus mu2 with a standard deviation of this formula. Okay, so here is that formula applied with the specific values plugged in. All right, we have 331 individuals who did receive calorie information with consumption, average consumption of 755 and a standard deviation of 241.1. For those who did not, we've got 306 individuals with an average of 816 and a standard deviation of 246. And so now we just plug all that stuff in. So our sample estimate is x bar sub 1 minus x bar sub 2 is 755.1 for those who did not get calorie information. I'm sorry, for those who did get calorie information, minus 815.9 for those who did not. And so we do have a negative difference. Now the question is that negative difference statistically significant? Our null hypothesis value is 0. Our null hypothesis says that the means are the same. And when we plug in values for S1, N1, S2, N2, into this standard deviation formula, we end up with an estimated standard deviation for the difference of 19.3. Computing our z-score from that, all right, the sample mean minus the null hypothesis mean divided by the standard deviation, we get minus 3.15, and therefore we're going to reject the null hypothesis that there's no difference because minus 3.5 is less than minus 2.33, which was our the z-score corresponding to our alpha of 0.01. All right? Okay, now, so for our consumers of this test, the people who are interested in the results of this test, we might write this up in the following way. We can say participants who received calorie information consumed on average 61 fewer calories than those who did not receive calorie information. And this is a reduction of about 7%. The difference is highly significant, alpha of 0.01. We can thus be confident that providing people with calorie information in this form is effective in reducing calorie consumption. Whether providing such information on the menu display would be similarly effective is uncertain. Okay, so notice that we have used a bit of critical thinking here to contemplate why our carefully controlled test might have produced different results than just giving everybody information right on the menus. Okay, now let's take a look. Oh, one other thing here. We used z-scores in this analysis so that we could just describe the algorithm without worrying about z-score versus t-score. We should really use t-score, but in this case, our degrees of freedom is so enormous that the difference between the t-score and the z-score is basically non-existent. Let's take a look at how we can do this comparing two means in the actual data set in aisle. So this is our fast food experiment. Here's our data. And in the toolbox now, the test we're going to perform is a 2-sample mean test. I'm going to go ahead and leave this set at the t-test rather than the z-test because the t-test really is the thing we should be using. The variable whose means we want to compare is total calories. And we're going to subdivide our population into 2 separate populations based on calorie information. Okay? Now, we are using a null hypothesis that the difference between the two means is 0. Our significance level is going to be 0.01. And our direction is going to be the left-hand tail. All right, so now we'll do our calculation. And let me scoot my toolbox over a bit. Interesting. Well, I guess we can sort of read that. Okay, whoop. Let me go back to this slide that had the numbers computed sort of by hand. All right, so our hypothesis is our null hypothesis is that there's no difference in calories consumed based on calorie information. But our p-value is tiny, 0.0009. We didn't actually bother to compute a p-value over here. And the test statistic is minus 3.1495. Here we just rounded to 3.15, minus 3.15. The degrees of freedom is 629. And with a degree of freedom that high, the distinction between the normal distribution and the t-distribution is almost meaningless. And we do reject the null hypothesis at the 1% level. Okay, so that's how you would go about setting this up in ISLE. Okay, so that was examples of testing the statistical significance of difference between population means. Now we're going to take a look at the difference between population proportions. The analysis is basically very similar. The only thing that's different is how you compute the standard deviation involved. Instead of this nasty formula, square root of the sum of the variances, we use a different, slightly less nasty formula. And because we're comparing proportions here, and the proportion is dictated by, or the standard deviation is dictated by the proportions, we are completely correct in using the normal distribution in this case. All right. So, question, did disapproval of Donald Trump increase from late March to late June of 2020? All right, so we'll label P1 as the proportion of likely voters who disapproved of Trump in late June. P2 is the proportion of likely voters who disapprove in late March. And we are, as our null hypothesis, going to assume that there was no change. The proportion in late June minus the proportion in late March is 0. Our alternative hypothesis is that disapproval rose. That is, the proportion that disapproved in June minus the proportion that disapproved in March is greater than 0. We're once again going to use an alpha of 0.01, which is a very strict test. And our z-score for a one-tailed test with alpha of 0.01 is 2.33. All right. All right, so according to a poll, the proportion of people who disapproved of Trump in late June was 0.57, whereas the proportion who disapproved in late March was 0.51. So the increase in disapproval proportion from late June relative to late March is 0.06. And the question is 0.06 statistically significant at the 0.01 significance level to indicate a decrease in approval? Alrighty, well, our z-score is computed using the same general formula that we always use. We've got the sample estimate minus the null hypothesis value divided by the standard deviation of the sample. P1 hat, in this case, is our estimate of disapproval at end of June. P2 hat is our estimate of disapproval at the end of March. And therefore, P1 minus P2 is an estimate of the true change in the true change in disapproval rating. Now, the standard deviation, well, to compute the standard deviation, we treat both populations together, and we compute basically a mean standard deviation, where p hat here is the number that disapproved at the end of June plus the number, or sorry, the proportion that no, I take it back again. The number that disapproved at the end of June plus the number that disapproved at the end of March divided by the sum of the two sample sizes. In other words, this is the mean proportion for the two samples. And the standard deviation then is p hat times 1 minus p hat times the sum of 1 over n1 plus 1 over n2. And this, again, is basically just kind of follows from, whoops, you know, from the mathematics of this. All right, so the average proportion of people who disapprove between late March and late June is the sum of the proportions that disapprove times the sample sizes divided by the sum of the sample sizes. And that's 0.54, which means that our z-score is 0.06 minus 0. Okay, 0.06 minus 0 is the sample difference, the observed sample difference minus the hypothesized difference, and we divide that by this computation and get our z-score of 2.93. And because 2.93 is greater than our 0.01 significance z-score, we conclude that there was a significant increase in disapproval of Donald Trump during that 2-month period. All right, let's take a look at another example here. Israeli HMO, is that Maccabi? I think Maccabi covers around a quarter of the 9.3 million people in the country. We compared results from 149,144 people over 60 who received their third dose at least a week ago from against the 675,630 who had received only 2 doses between January and February. And what we're interested in knowing is the Pfizer booster shot effective in reducing COVID infection compared to only receiving the original 2 doses that were prescribed for that Pfizer COVID shot. Okay, 37 people tested positive for COVID after their third shot. In the U.S., we call these shots, and in many other places, they're referred to as jabs, compared with 1,064 positive cases among those who only received 2 doses. The comparison groups had similar demographic profiles. So, in other words, we have, okay, so we've got the proportion of positive among the people who got their third jab. Let me make sure I'm using consistent notation here. So Okay, so we're going to have P1 be the proportion positive among 3-jab people, and P2 is the proportion positive among 2-jab people. Our null hypothesis is that there's no difference, that P1 minus P2 is 0. Our alternative hypothesis, H1, is that P1 minus P2 is less than 0. In other words, that a lower proportion of people who have had 3 jabs are positive compared with the proportion who only had 2 jabs. We are going to use an alpha of 0.01, which in turn implies that our critical value is Z sub A is 2.33. This time on the left side. Okay, and our proportion, P1, is equal to okay, 37 people out of 149,144. P2 is 1,064 positive cases out of 675,630 who only received 2 jabs. That means that our P hat, from which we're going to compute our standard deviation, is the number of positives in both populations divided by the total size of both populations. Okay. Which, that, okay, the number of positives divided by the total number of people is equivalent mathematically to the proportion positive times the number of people who had 3 jabs plus the proportion negative, or the proportion positive times the number of people that only had 2 jabs over the total number of people. So those are equivalent computations. And now we're going to compute our z-score. So our z-score, and I'm not actually going to run this out all the way to numbers, but our z-score is, well, okay, so it's P1 minus P2 over p hat times 1 minus p hat times 1 over 149, 144 plus 1 over 675, 630. Square root of all of this stuff. Okay, so all of this stuff to the 1/2 power. Okay, so there's how we would set things up. I'm not actually going to compute all these numbers, but there's how we would set up to determine whether 3 jabs is more effective, is statistically significantly more effective than just 2. All right.